Welcome everyone. Welcome to this particular module, Unit 2 we are discussing, and today we will see the construction of SCR. SCR full form is Silicon Control Rectifier and the commutation in SCR. So let us start. So if we see the basic construction of SCR, it almost looks like a diode. If you look at the symbol of the SCR, it almost looks like a PN junction diode, where the positive side we call it as anode and the negative side is we call it as a cathode, and from that cathode side we have one more terminal which is called the gate terminal. So SCR is a three terminal device. Now, this is the construction of the SCR. It consists of a alternate PN-PN layer. That means it is a 4-layer power semiconductor device where the top side P layer is connected to the anode terminal through a metallic contact. Bottom side N layer is connected to the cathode terminal through a metallic contact, and before this bottom side N layer there is one P layer. So from that P layer we are connecting the gate terminal through a metal contact. So you can also visualize this PN 4 layer device as if two PN junction diodes are connected back to back. Also, we can also visualize it as one PNP transistor and another NPN transistor. They are connected together. So for this PNP transistor, the top side of this, the top P layer is connected to the anode terminal, and the N layer of this PNP and NPN transistors are connected together, and the P layer of this PNP and this NPN, they are connected together, and the bottom N layer we are taking the cathode, and these two P layers are connected together, right? So from that P layer we are taking the gate terminal. So we can also visualize this structure in this manner. So here this is one P. If we draw it or if we want to represent it in terms of symbols, this is one PNP transistor. Obviously the direction of the arrow, by observing the direction of the arrow we can tell this is a PNP transistor and this is an NPN transistor. The base of this PNP transistor is connected to the collector of the NPN transistor, and the collector of this PNP transistor is connected to the base of the emitter transistor. Okay, now we will see, as we apply different battery voltage between the anode and cathode terminal, how this SCR conducts, how this SCR operates. So as we have already seen in the basic construction, it is a PNPN 4-layer PNPN device. The top side, the top P layer we are taking the anode, bottom N layer we are taking the cathode, and between anode and the cathode we are connecting a battery. Okay, this battery is connected as the reverse bias. As you can see, this is connected as a reverse bias and we are calling it as V in. Okay, and from this P layer the gate terminal is connected. So far initially we are not giving any gate pulse, so a reverse bias voltage has been applied. So now this is a 4-layer device. How many junction is there? This is one junction, one PN junction. This is another PN junction. This is another PN junction. So total 3 junctions are there. Let's name it as J1, J2 and J3. Okay. So at this biasing condition, what will happen? J1 will be reverse biased, because P side is connected to the negative terminal of the battery and N side is at higher potential. So J1 will be reverse biased, and we know when a PN junction diode is reverse biased means it is off, it acts as an open circuit. Okay, let's see what happens to this J3 junction. N side is connected to the positive terminal of the battery and P side is at lower potential. So J3 junction is also reverse biased and it will be open circuit. What about this J2 junction? See, J2 junction, this N layer is connected to the negative side of the battery and P side is at higher potential. So J2 junction is only the forward biased, and when PN junction diode is forward biased, we know it is on and it acts as a short circuit. But this J1 and J3 are open circuit. It is reverse biased. Okay. So very little as we know, when the PN junction diode is reverse biased, very little current, minority charge carrier current, flows through this SCR. Okay, minority charge carrier current will flow through the SCR, because due to this open circuit, we don't have it, the circuit is disconnected from here, the circuit is again disconnected from here. So due to this reverse bias voltage, a very small minority charge carrier current flows through this SCR, and this current we will call it IAK, anode to cathode current. So if we plot these IV characteristics in this reverse bias condition, how it will look like? This is the negative voltage that we are applying here, minus V in, which is in volts, and this anode to cathode current is also negative, which is in microamps. So for a lower value of V in, what happens? Very small, as we keep on increasing this V in, very small current, anode to cathode current flows. Okay, J2 junction is what? It is forward biased. Now if you increase this V in, at the breakdown voltage, reverse breakdown voltage, what will happen? See here, we have a J1 and J3 are reverse biased, right? So the depletion region at the J1 and J3 are large. So if we are apply very high, we know that as we keep on increasing the reverse bias voltage, depletion region with increases. Now if we apply a very high reverse bias voltage, then the certain limit, it will cause breakdown in the depletion region existing at the J1 and J3. Okay, and the depletion region will get vanished, and the J1 junction and J3 junction, it will act as a short circuit, and the current will start, huge amount of current will start flowing through the circuit. So this is the breakdown voltage that you have applied here, and once you apply the breakdown voltage, this J1 and J3 depletion regions are getting removed, and your current will start exponentially increasing through the SCR. Okay, and if you apply more voltage than this voltage, reverse bias voltage, your SCR will get damaged. But it is a very dangerous situation to apply this amount of high reverse bias voltage to remove the depletion region. We are not supposed to do that. So in this mode of conduction for SCR, it is called the reverse blocking mode. Okay, next, see, next type of, what is the next conduction mode? Next conduction mode is the forward blocking mode. Let's see what is that. So here what's new, we are observing the polarity of the battery has changed. Now this anode is connected to the positive terminal of the battery and cathode is connected to the negative terminal of the battery. So in this condition, let's see what will happen to the biasing of this J1, J2 and J3. For this J1, P side is connected to the positive terminal of the battery and N side is at lower potential. So J1 junction is forward biased, means it is short circuit. J3 junction, N side is connected to the negative terminal of the battery and P side is at higher potential, right? So what will happen in this case? J3 junction will be forward biased and it is short circuited. What about this J2 junction? In this J2 junction, N side is connected to the positive terminal of the battery and P is connected to the lower potential. So J2 junction is reverse biased. So since this J2 junction is reverse biased, the supply V in, it is breaking here. The supply can't reach here. So once the supply can't reach at every junctions, this anode to cathode current can't flow through the circuit, and your SCR, it will remain in the off condition. Okay. So since J2 is reverse biased, at reverse bias we know very little amount of minority charge carrier current flows. So this is the current. You are increasing this V in, but since J2 is reverse biased, a very small minority charge carrier current you will get. And this, in this mode, your SCR, it works in the forward blocking mode. Okay. Now, if I'm increasing this V in beyond a certain limit, very high limit I'm giving, very high V in I'm giving, what will happen? This J1 and J3, it will remain as it is forward biased. Under forward biased, we know that width of the depletion region is less, and if the electrons and holes in this P and N regions, they have enough energy, they can overcome this depletion barrier existing at J1 and J3 because they are forward biased. But what about this J2? A huge depletion region is existing here due to this reverse bias. So at this condition, if we increase this V in more and more, that means I'm increasing this reverse bias at J2 more and more. So at this condition, what will happen? Beyond a certain limit, the depletion region existing at J2, it will break. It will cause a breakdown in the depletion region, and J2 will become short circuited, same as J1 and J2, and huge amount of anode to cathode current will start flowing through your SCR, and your SCR will come to the conduction state. Okay. That means there is a way that if we increase this anode to cathode voltage, we can cause a breakdown at the depletion region existing at the J2, which where the width of the depletion region is very high, and the depletion region will get vanished. Okay, so this is a way of turning on the SCR, but this should not be followed to turn on the SCR, because if it happens, your SCR will get damaged. Okay, so what is the way out? So far we haven't applied this gate terminal. Now let's see if we apply this voltage, if we can create a voltage difference between this gate which is connected to this P layer and the negative of this battery is connected to the K layer. So a gate current will start flowing in this way, and it will flow in this way. From this P to N, it will flow in this way. Okay. Now once the gate current starts flowing into your SCR in this way, what happens? In N region, in the bottom N region, we have free electrons. So among the free electrons, the electrons that are having higher kinetic energy, they will start traveling in the reverse direction. And when they reach at the J2 junction, they will attack this depletion region existing at the J2, and it will cause a breakdown in the depletion region. The more you increase this gate current, more number of free electrons with higher kinetic energy, they will attack this depletion region, and it will cause a breakdown in the depletion region. Okay, and your current, anode to cathode current, it will increase. So in this case, what happens? We don't even need to apply that much of high V in that we were applying earlier, because we are increasing this gate current, no? So we don't need to apply that much of high V in now. So this much operation we have seen in the last slide, that when this J2 junction is reverse biased, for a smaller value of V in, when we didn't apply this gate pulse, we are getting a minor current due to the minority charge carriers, and this region is called the forward blocking mode. But without applying this gate voltage, once we are applying a very high amount of V in, at which it causes a breakdown in the depletion region at J2, huge amount of anode to cathode current starts flowing through this SCR. Okay, so you can see that voltage of V in is called the forward breakover voltage, represented as VBO. So once you apply this VBO, what happens? VBO we are applying here, right? V in. What happens? This depletion region at the J2 junction, it gets vanished, and huge amount of anode to cathode current we are getting. Okay, you can see there is a drastic change in the anode to cathode current, and this happening when we haven't applied any gate pulse. Now once you start applying the gate pulse, what happens? This kind of, we don't even need to cause a force breakdown as we were causing in the earlier case, because these electrons, they will travel and they will attack this depletion region, right? So in this case, when you start applying this gate current, you can apply less forward breakover voltage to get the anode to cathode current. So you can see here forward breakover voltage, that means you are now applying less V in once you have started applying the gate current, and at that condition you will start getting conduction through the SCR. That means you will start getting the anode to cathode current. You apply more gate drive, you apply less forward breakover voltage, your SCR will start conducting. You will start getting conduction from this point. Even if you increase this gate current more and more, what will happen? You need to apply less V in and your SCR will start conducting. Okay, so this VBO, forward breakover voltage, when we didn't apply the gate drive, it is higher than this one, VBO1, then it is higher than VBO2, then it is higher than VBO3. Okay, similarly this Ig0 is less than Ig1, less than Ig2, less than Ig3. As we keep on increasing these gate drives, Ig0, Ig1, Ig2, Ig3, what happens? At lesser voltage of V in, we start getting conduction, anode to cathode current. Okay, so this region of operation, that means after applying this forward breakover voltage, when your SCR starts conducting, that is called the forward conduction mode. Okay, and once you apply the forward breakover voltage, your SCR start conducting, right? You start getting the anode to cathode current. The minimum value of this anode to cathode current at which your SCR gets turned on, that means it goes from forward blocking mode to forward conduction mode, that current is called the latching current, represented as IL, and the value of this latching current is 10 to 30 almost milliamps. Okay, now there is another current called holding current. If you decrease this V in, what will happen? This anode to cathode current through the SCR will start decreasing. So when this anode to cathode current start decreasing, and the minimum point till which it gets turned on, after which it enters from the forward conduction mode to forward blocking mode, that anode to cathode current is called the holding current, and it is represented as IH, and the value, the range of this IH is 8 to 10 milliamps. The holding current value is always less than the latching current. So this is all about the three conduction mode of the SCR. Now let's see what is commutation. The process of turning off the device is called the commutation. Commutation can be two types. If we are discussing the commutation in SCR, it can be natural commutation, another one is a force commutation. So in case of natural commutation, if we consider, this is the halfway rectifier circuit. Okay, so input voltage for natural commutation, we give the AC supply. Okay, so what happens? This is a halfway rectifier, so this signal I am applying at the input side. So during the positive half cycle of the input signal only, diode is on. So the output voltage that is appearing across the load, it is same as the input voltage, or the output current is same as the input current. Okay, and that means only during the positive half cycle of the input signal I am getting the output. Now what happens if I am applying the negative half cycle of the input signal? Diode is off because it is reverse biased and we won't get any output, okay, during the negative half cycle of the input signal. That means this circuit can be naturally turned off if we make this diode reverse biased. So this kind of commutation is called the natural commutation. Next, another type of commutation is forced commutation. Forced commutation means in this case we need to apply DC voltage as the input and we can't turn it off naturally. So we need to take the help of some external circuit to turn it off. Okay, this type of commutation is called the forced commutation. So this forced commutation is also classified into 5 types. One is class A, class B, class C, class D and class E. So in these different classes we use mainly the LC oscillation circuit, and the oscillator circuit, LC oscillator means inductor capacitor oscillator circuit. It is controlled in such a way that means your oscillation, when it reaches to such a particular point that where your current flowing through the SCR becomes zero, then the SCR can be turned off naturally. That means we need to take help of some external circuitry. That is why it is called forced commutation. We can also have some, we need to also use some auxiliary SCR, some secondary SCR we need to use as a control circuit to turn off the primary SCR. So this is all about the commutation of SCR.